Okay, so we are back. So this figure here, figure A, B, and C. Okay, showing this is now just look at it this way. This is showing you a fixed end, right? Built in. So when you see this kind of design here, you know that it is what? A fixed beam, right? This is what? A roller, and this is what? A pin. Okay. Now, assuming, let us just assume something. Assume that figure B is joined to figure A, and figure C is joined to figure B. All of them are joined together. You know that you have an extra, a hanging over figure C, right? Figures, it will be, the beam will extends beyond figure C. So if you have that kind of a beam, what do you call it? An overhanging beam. Overhanging beam. That is, it extends beyond a support. It extends beyond a support. Okay. Internal forces in a beam. So the internal forces in trusses were simple as they only carry axial load. Beam members, however, carry multiple loads. I even talked about trusses here, but okay, it's okay. Let's go. Axial loads. Axial. That is, if we look at this beam, assume this beam is now the loads P and P are now acting at the ends. Either pushing the beam into together or pulling the beam apart. If it is pulling like this, and look at this figure, look at the forces acting at the what? At the neural, what do you call it? Neutral axis, right? These are kind of what? They are pulling, stretching out. If it's stretching, that means what? Tension. But if it is pressing towards, it means what? Compression. Tension means pulling out. If you have a rubber band, and you're pulling it, means you're what? You're tensioning the rubber. And then you have a loaf of bread and you press it from the end, like you guys do when you're eating bread with beans. You press it this side, it means what? You're compressing. Shear forces, that is acting at angle 90, perpendicular, you know, and then bending, trying to twist it, trying to turn over. Let's go. Okay, and you know very well, you know vector quantities and what? The second one is what? We have vector quantities and what? Someone should tell us. Scalar quantities. Now, what's the difference between the two? Vector and scalar quantities. What's the difference?
One is having magnitude direction, the other is having only magnitude.
Vector quantities have what? Magnitude and direction. A force may act in any direction, but resolved into what? Vertical Y and horizontal X components for convenience. Right?
Yes, sir.
Okay. So state of equilibrium says what? The state of equilibrium requires that the sum of the vertical components and the sum of the what? Horizontal component must equal what? 0. Must equal 0. For you to have what? Equilibrium. Equilibrium means what? Steady. Okay. Moment or rotational force. So a moment is a force acting on a member that tends to cause rotation. Look at the word rotation. Rotation about what? Any point other than the point through which the force acts. The moment is due to a force acting at a perpendicular distance from the axis. Let's come back to this. Look at this too now. Look at this. See? You see this? You see, M is moment, V is what? Shear. Do you get? M is moment. These are trying to what? Make this thing to turn, twist. Right? Look at moment here again. Upward force, making this what? To turn this way. It's just like two people sitting on a bench at the ends of bench. And if one person gets up, what happens? The bench falls the person down, right? The person sitting at the other end, the weight now is the load, now tends to what? Turn the bench over, right? So that's why when two people are sitting on the bench, if one person is getting up, the second person tells what? Sit well. You know, that means what? Shift in. Do not sit at the edge. Else, what happens? The bench will turn over. Those are typical examples of what? Moment forces, right? Moment in a beam. I guess you guys know that a bench is a beam, right? A bench is a beam. And let me ask you guys now, what kind of connection do you have in a bench? Right? A bench that you can move. What kind of connection do you have at the legs of the bench to the bench itself? You know, the bench is a flat surface on which people sit. And then you have the legs. The legs are now the support. Where people sit is a beam. The legs are the support. Now, what would you call this? Look at this. Let's look at this diagram. Good. Is it fixed or built in for a bench? The support, are they fixed or they are built in? Are they what? Roll-up, bearing, or are they pinned or hinged? Which one is the correct answer here? A, B, or C? In a bench that all of us know.
Fixed. Pin.
Pin is correct. Why is it pin? Because they are nailed. Right? They are nailed. Okay, let's go. Okay, so we are here now. When a beam remains stationary and is in equilibrium, the sum of all the horizontal forces acting on the beam, the sum of all the horizontal forces acting on the beam is equal to 0. The sum of all the vertical forces acting is equal to 0. The sum of all the vertical forces is equal to 0. And the sum of all the moments acting about a point is equal to 0. Any of the following combination of equations expresses a state of what? Equilibrium. This is it. That is, a bench is sitting. There is no force pushing it from the side to move. There is no force pushing it from up downwards to break. There is no force acting at the edge of the bench to turn it over. So since all those forces are equal to 0, it means what? There's no movement. The bench is not going to shift. The bench is not going to turn over, which is moment. And the bench is not going to fly upwards, which is what? Vertical. X means the bench is not going to slide. Y means the bench is not going to fly up or crash to the ground. That's what? Y. And then M is what? The bench is not going to turn over in any way. So as long as the forces are 0, it means what? the bench is in equilibrium. Understood?
Yes, sir.
Okay. So just let us note what we have here. He says what? Maximum compression, FC, occurs in the section where the bending moment is maximum. You understood? Maximum compression occurs where the bending moment is maximum. In the design of simple beams, section modulus Z should be selected such that FC does not exceed the allowable value. Allowable working stress values can be found in building codes of engineering. Yes. You have that in the note. Let me open the note and show you. Do we? Let me check. Check. I guess it was there at the time, yeah. I hope if you are still there with me, you should not go anywhere. Good. Let me see. I'm coming on. Okay. I think I'll show you guys later. Okay. And this is what he's saying. For safety, the whole of this thing here, it says what? It says, okay, in this design of simple beams, section modulus Z should be selected such that FC does not exceed the allowable value. Allowable working stress values can be found in this. So this one here, this is FC. Allowable. Now we'll make this small letter. I'll make this small letter. Good. And what is your section modulus? Who can tell us the equation of a section of section modulus? Section modulus, who can tell us?
I over what?
Eh? You said what? Okay. This is
I divided by Y.
This is section modulus of a rectangular shape. It's either Z or S. Depends on what you want to. Right? This section modulus for a rectangular face, for a rectangular cross section. Right? Right? Hey, what's that? And it's saying that what? FC does not exceed their allowable value. So look at it here. FC is your design value. FO, this is your allowable stress. Let me do this so that you know that this is FC. F allowable. It means what? It says, where can you get your F allowable? It says allowable working stress. That is your F all, F allowable. Let me put it here so that you will get it. Yes? I hope you guys are following me.
Yes, sir.
Okay.
Yes, sir.
Good.
Yes, sir.
Okay. Are you people tired, me? Right? Understood?
Yes, sir.
Okay,
Yes,
so now
sir.
the next slide here. The next slide here is showing us a cross-sectional modulus. Oh, no, this is showing what? Okay. Loading, bend. Okay, good. This is not, we've not got into cross-section. You should have that one to close by. Let's have that close by so that we'll be following everything systematically. Copy now. Oh, no. Okay. Good. Right. So I want to show you guys the cross and the sectional modulus of once we finish this portion here, next class we'll just be following through the note, going through the note, because some of those things I can't move them to PowerPoint. Oh, I just think wasting my time now. All right, so any questions so far? Any questions? Any questions? Huh? What's this? What's this? Any questions? Finn, any questions? I know you say no questions now.
Sir, can we get the material, sir?
Haven't I given you the notes before? I gave Finn.
No questions, sir.
Finn.
I haven't seen this material.
Which material?
See, this one is different from the one I have, sir.
Which one are you talking about? You mean the PowerPoint?
Yeah, this one you are using exactly. There's one of 100 pages. It's different from this one.
I know. I'll send it after this class.
All right, sir.
So once we finish this portion, next class we'll be following the note. This is just introduction. So, okay, good. So let's just continue. Okay, this table here is showing us the bending equations. Beam, okay, good. Beam equations. Diagram here is showing you what the conditions, right? Here is a pointed load or point load, both from up and down. You can see that, and these are the shear equations. This is the shear equations, right? The bending moment equations that you have here, and then the deflection, right? So basically, let me give you guys CO. AC rather, AC, right? What you should basically look at here, what the diagram, the beam designs that you should look at, study hard to know are the first two. I said the first two, right? I hope you guys are following me.
Yes, sir. Yes, sir.
Yes, sir.
I say only the first two that you have here, only the first that you should study hard to know, right? Okay, so let's go on. Then let's go horizontal shear force. Okay. Acts tangentially to the horizontal cross-sectional plane. The average value of this shear stress is this. A is a transverse cross-sectional area. Good. A, like I told you before. A, okay, now for a beam, I told you guys to buy what? A 2x4 and what? A 2x2. 2x4 is telling you what? The surface, the cross-sectional area, the cross-sectional dimension of the beam. So if for a 2x2 beam, the cross-sectional area is what? 2x2, that is a square now, right? That's 2 times 2. That is what? 2 millimeters squared, depending on your unit. Then for a 2x4 beam, the cross-sectional area is what? 2 times 4, which is what? 8, whatever the unit squared. So look at it for horizontal shear force. These are for the different shapes. For a rectangular shape, this is what you have, B times D. And then let me ask you, look at this, for a square section, you have here what? A squared. That small A squared is standing for what? 2x2. Since it is 2x2, you can, instead of saying 2 times 2, you can say what? 2 squared, right? That is it. And there's something wrong with this. This is not supposed to be 3/3. It should rather be what? Who can tell us? It should not be 3/3. It should rather be what? 3/2. This should be 3/2. That's it. That's why you know it's good to be in class. Those people are not in class now, if they go to exam and go and do 3/3, and then the answer, you see, is to be wrong. For a circular cross section, you know the area of a area of a circle. How did we arrive at this? What's the area of a circle? What is the area of a circle?
Pi r square or pi d square over 4.
So if you resolve it and arrive at this, or what we have here, and then forget about this I section. Okay, we have finished this PowerPoint. Oh, no. Oh. Why was it not showing? Okay. Oh. Oh, this thing don't too good. Good. This one's here, this portion here. This one should not be here first. It should not be. This one should be. This one should be up. This one should be up here. Good. So let's start with this so that we'll continue next class. Deflection of beams. Excessive deflection cause what? Cracking or what? Cracking of plaster in ceiling, or can lead to jamming of doors and what? Windows. That's why you see some sagging ceilings in the house is due to what? Excessive deflection. You see some doors will not be able to close anymore, and you call a carpenter to come and file it up or slice it up again so that the door will be able to close. That's excessive deflection. It usually happens during dry season when the wood over dries, you know. And then you have most building codes limit the amount of allowable deflection as a proportion of what? Of the member's length. So look at, these are the allowable deflections. So now, in most times, allowable, you guys should listen. Allowable deflection means what? What can be tolerated. What can be what? Tolerated. That is what? Allowable. Or you can as well call it what? Tabulated deflection. That is, it is already given to you in a table. And just as you have your 4-figure table. Now, when you have design deflection, that is the one I will give you a question and you are going to design, use this formula, use this equation to calculate. Let me show you. Use this equation here to calculate. But you guys should forget about this equation, it's too complex. There's a simpler one. So these are the allowables. And for your design to be correct and to be safe, your allowable deflection must be what? Greater than what? Your calculated deflection. Understood?
Yes, sir.
And as well, your what? Allowable stress must be what? Greater than what? Your calculated stress. Yes. So steps in the design of a simple beam. 1, calculate loading on the beam. If you have point load, you are all right. What do you need to do? You just need to calculate your what? Your reactions from the 2 supports. But if you have a note this, if you have a uniformly distributed load over a platform, you must resolve the uniform distributed load to a what? To a point load. Number 2, that's why it says what? Calculate loading on the beam. Is the loading point load? Point load, fine. You don't need to do anything. But if it is uniformly distributed, that means what? It's either by length or by area. You can have, very good. If we spread Gary on a platform, if we spread Gary on a platform, that means the weight of the Gary is spread over a surface area, right? So now, for you to, that means the weight of the Gary is now over a surface. That is going to maybe 10 kg per what? Meter, per meter squared, right? So for you now to resolve this 10 kg per meter squared or 10 kilonewton per meter squared into a point load, what do you need to do? You're going to multiply by area. What area? The area of the surface, total area of the surface. Per meter square, you have 10 kg. So the total area of the surface, you're going to multiply by the total area of that surface. You get? To resolve it into, by the time you multiply 10 Newton, this guy's going to end again. 10 Newton, we're going to finish now in 10 minutes. 10 Newton per meter square multiplied by area means what? Area, meter square will cancel meter square. So you're going to have what? 10 Newton. Understood? Number B,
Yes, sir.
calculate the bending shear forces. C, for the maximum bending moment and max, provide a suitable section. This is it. Check for shear stress, deflection, and buckling. And buckling of web, forget about buckling of web, if necessary. Very good, say if necessary is there. And then this for deflection, this thing just jumped. Okay, so, oh, no. So this way we're going to stop using this PowerPoint. If I were to be physically available, we can do that. So now, here comes the end of this using of this PowerPoint. What I'm sending it to you, Fee, I'm sending this to you now so that you share it. And then in the next class, screen share has to, okay, good. Next class, we'll strictly use this note. So next class, you guys should come in with you should have your notes handy so that we will so that you guys will be following me as I go over the notes. Understood?
Yes, sir.
I have recordings of this thing, but how to share is a problem. Maybe I'll try to share using Google Drive or something here. Maybe you can get that. Finn, I forwarded the PowerPoint to you guys now, so share it immediately. Share it now. Finn. All right. Are you seeing my screen? Are you guys seeing my screen?
Yes, sir.
All right. So let me show you where we're going to start. You guys should please help me now. Read ahead of class. Read ahead of the class. So we're going to start here. Beam design. You are seeing, right? Can you see?
Yes, sir.
We are going to start beam design.
Yes, sir.
We'll do this beam design. So I want us to take it step by step here, so that from these points we know how to calculate the reactions and all that, so that by the time we start the proper thing, we'll not have issues. So you guys should please, I beg, you should just read ahead, right? But next class is going to be on Tuesday, not on Wednesday again. Next class is Tuesday, 9 a.m., right?
Right, sir.
Okay. So, any questions? Any questions? Any questions? No questions. So, I'll see you guys next week. Right?
Thank you, sir.
All right, sir. Thank you, sir.
Yeah, see you guys. See you guys.
Thank you.